Aloha, Richard Halverson here. This is ITS148, and today I'm going to do project 19.5. So let me share my screen. And so here we are, and I'm going to do 19.5. So if we look at 19.5, let's open it up. And in this problem, we're supposed to modify we have this MyBST class that we're creating that extends the regular old BST class. And what it does is it adds this method. And what this method does is it checks to see if it has the same shape as some other tree. Okay. And by same shape, it just means the same structure. It means like if there's a left subtree and a right subtree, they're exactly the same. They don't have to have the same values in the nodes, but they just have to have the same structure. Okay. So a test of two trees have the same structure. They might have different numbers inside the nodes or something, but the same number of nodes and the same configuration of nodes is the same. All right, so it gives us this. In fact, I'll tell you what. Why don't I draw some? Okay, so we have like this can be something. I can put another one down here. And this is the same structure as this. Obviously, regardless of what's inside these nodes, okay, and so what's inside these nodes can be anything. Okay, so it's just structure. Let's do something like put. All right, so let's see what they give us to start with. Copy. And they give us BST, of course, and down here they give us the tree node, and here's where we write code. And okay, so it's got this this is the method that is accessible from the outside. So this is the one that you would call from down in your main program. Has same shape, and has same shape uses this method that you're going to write called is same shape, and it looks at two different trees and returns if they're the same shape. And again, now this is a recursive. We're going to write this as a recursive function, which basically it uses itself. It defines what is returned in the most minimal case, and then everything else. Then for and since a binary search tree is recursively defined, then you're able to traverse through both sides of the trees down the line using the same recursive method. And it's going to always stop because it's always going to hit a stopping node. It's going to hit a node with no leaves, okay, and then that stops it. It's either going to hit a node with no leaves or nothing, okay, a branch to nothing. And those are the cases that you handle by returning something, and then so that makes it so your code does not go into an infinite loop. Okay, so let's grab this. I'm going to do Control A, Control C, and go over here and I'm going to do Control V to paste it in. And let me save this. And what we're going to write is this, is same shape. Okay. And so that looks something like this. So we're testing R1 and R2. Now, if R1 is none and R2 is nothing, then by God, they're the same. Return true. Okay. Now, if R1 is equal to none, or R2 is equal to none. Now this is tricky. Let me explain this to you. Then return. Okay. And then else. Now, so if R1 and R2 are equal, if R1 is equal to none and R2 is equal to none, then that's taken care of in this case. If it gets down to here, then we know that either R1 was not none or R2 was not none. Okay, we know that. We know that because if they were both none, then it would have been caught up here. So we're down here, and we know that at least one of them is not none. And then then we test if one of them is none. It doesn't matter which one it is. If one of them is none, then we know the other one is not none, because if this one is none and the other one was none, then it would have been caught up here. So anyway, so that's why we know that if at this point, if either one of them is none, then we know that they're not equal, and so we return a false. Otherwise, if both of them are not none, then we want to say the left node is no, we want to okay, left shapes. Okay, so so we have this R1. It's got R1 has got a let's see, return. I can go right to return. Self is same shape. I'm going to use, so this is my recursive call of R1 left, R2 left. Okay, so so at this point we have to have a way of testing if R1 and R2 are the same, and there's something there for both of them. So the way we know that they're the same is there's at least one node there. We first have to test to see if R1's left tree is the same as R2's left tree. And so that has to be true. And self is same shape R1 right has got to be the same shape as R2 right. Okay, so what this means is we start out here. Let's see, we start out, I'll use this color. We start out here, and we know that this is self. Okay, this one will be self. And this one is tree. And we're testing to see if they're the same. So So the first, so we're testing to see if they're the same shape. If R1 is the same as R2, I guess I can call this R1 and this is R2. Is it true that R1 is equal to none and R2 is equal to none? No, it's not true. So if we drop down here, is this true? No, neither of them is none. So we're at this case, and so then here we're going to test if the left side of, okay, so then we're going to test, is this side equal to this side? Okay, and that's this first one. And then this one over here is test the right side. Test the right side with this right side. Okay, test if these are the same. And the first one tests if these are the same. And so the way it does it is first it has to, test if this left side and this left side with this right side, and then it keeps on going down, and it gets here, and this has a left side of none, and it has a right side of none, and lo and behold, this one too does too, left none, right none. So they're the same. So the left side of this is the same as the left side of this, and so on. So that's how this recursive testing, it keeps on testing each node all the way down, and it's mirroring itself. And as long as it continues to be mirrored, as long as we're returning true, then it keeps on going. But once it returns false, then it'll just continue to return false, because if this returns false ever, this is going to be down at the bottom. This is going to be down at the bottom somewhere. Then this returns false, and that means that one of these ends up being false, either this one or this one. And with the AND function, only one of them has to be false before this returns false. And so that's how the returning of false, once it figures out one side is not equal to the other side somewhere down the line, then that triggers false being returned all the way up because of this ANDing with this. So anyway, that looks pretty good. Let's save this, and let's just try to run it. So I can do pytest.py, and it says enter one line of the tree. So enter one. So let me just go back to this one. So I can just enter 4, 3, 5, and 7, 6, 8. 4, 3, 5, and 7, 6, 8. And it says they are the same shape, and basically what that is let me clear this. 4, 3 would be down here, and 5 would be here. That's one binary tree, and the other one is 7, 6, 8. 7, and then one down here is going to be 6, and then 8. And yes, they are the same shape. So anyway, okay. I think that should get you going on 19.5. All right. Thanks for watching.